Greetings, Gen Chem students. This is our fourth and final video introducing the demonstrations of atomic line spectra. And in the previous one, what we did, if you recall, we took metals, different metals, copper, strontium, and sodium, and dissolved them in alcoholic solution, sprayed them into a flame. The heat of the flame excited those atoms, and as those atoms went up into high energy states and relaxed back down, they emitted light of very specific discrete wavelengths, lines of wavelengths of light, and different colors. And what that illustrates, that illustrates that the energy of the atoms are quantized, that they can only exist in very specific energy states, because very specific colors of light relate to very specific wavelengths. A very specific wavelength of light will have a very specific frequency, as indicated by the fact that frequency is equal to the speed of light over wavelength. And then a specific frequency gives a very specific energy, since energy, according to Max Planck and Einstein, is equal to h nu. So very unique colors of light are demonstrating very unique energies that are coming out of that, those particular atoms. And we saw strontium emitted red light when it was excited, copper emitted green, and sodium emitted orange. And so we're going to see this line spectra again, but only for sodium. And when I do that in this way, let me move this about a bit. Through this demonstration, we have a jar of pickles here, and pickles are simply cucumbers that are soaked in salt, sodium chloride. So this pickle contains lots of sodium because it's saturated with sodium chloride. And what we're going to do is we're going to excite those sodium atoms that are in that pickle. We're going to excite them not with a flame, but with electrical energy. So I'm going to hook it up to this variac, this electrical power supply. And I have to be careful here. Never try this yourself. I'm protected by this big variac here. And you do not want to play around with this at home. If you don't kill yourself, you'd probably knock out the power of your house and maybe the power in your neighborhood. But let's get this going here. Okay, so I have a couple of metal forks stuck into that, pickle, and now I'm going to turn up the voltage. I'm going to hit it with electrical energy, tremendous amount of electrical energy, and we'll see what happens here. Oops, let me. And there you go. And notice that the light being produced here isn't it that same distinctive orange color that we saw when we excited the sodium atoms in the alcohol flame. And all you have to do is to excite a certain kind of atom and it will emit its very unique wavelength of light. And that is the line spectra, a part of the line spectra of sodium atoms. And we get a lot of smoke there as well. So, and we have a hot pickle. I'm going to turn out the light and see if you can see the orange color more distinctly. Okay, let's pump it with some electricity again and see if we, there you go. I think that's a little more clear. That yellow orangish light is that we saw before. So that's all you have to do to get an atom to show its line spectra is to excite those atoms, and as they drop back down into their lower energy states, they will emit their unique line spectra. And remember from the video lectures, it's unraveling the mechanism by which those line spectra are created that resulted in the Bohr model of the atom. And the Bohr model of the atom wasn't complete, but it led to wave mechanics, which gave us a complete understanding of the locations, the energy states of electrons within atoms, and not just hydrogen atoms, but all the atoms in the periodic table. And once we had that, we could determine the electronic structure of all the atoms in nature, and we could use those electronic configurations to predict and explain the properties of all the atoms in nature. And that's what we're doing in this section of the course with quantum mechanics and electron configurations, and beautiful stuff. But that's it for this little video. Come on, baby.